All right, chapter 7, section 3, proving a quadrilateral to be a parallelogram. This is essentially what we call the mirror image of the material that we covered in section 2. So let me take a moment to review what we did in section 2. Section 2, it was basically properties of parallelograms. We learned that a parallelogram was a four-sided figure whose opposite sides are parallel to one another, thus the name parallelogram. Pretty straightforward, but the important thing to learn from section 2 is that once I know a figure is a parallelogram, and in section 2, that's the fact that I began with. But if I know a figure is a parallelogram, then we learned 4 theorems that are true of any and all parallelograms. First, we learned that opposite sides of a parallelogram are congruent to one another. In other words, they have the same side length. So if I were to get out a ruler or a measuring tape, whatever it might be, and measure the length of each side of a parallelogram, the sides that were opposite each other have to be the same measurement. Right? They don't all 4 have to be the same measurement. That's a different kind of parallelogram, like a square or a rhombus. But the opposite sides, the sides that are opposite one another, do have to be the same side length. The second one we learned was that on the inside, there are 4 angles that make up that four-sided figure, that the angles that are diagonal to one another or opposite each other have to also have the same measurement. And this measurement would be in degrees. Then we also learned that consecutive angles, so again, in the 4 interior angles of a four-sided figure, angles that were consecutive or in a row next to each other, for instance, both angles on the bottom or both angles on the side, that sort of thing, they would have to be what we call supplementary to each other. Okay, supplementary again meaning that they add up to make 180 degrees. And then lastly, we learned that inside a parallelogram, that the diagonals that we can create inside that parallelogram, and there are 2, the 2 diagonals inside a parallelogram have to bisect one another. In other words, they chop each other in half. Okay, so that's what we learned in section 2. The reason I bring that up going in here into section 3 is that essentially we're going to be dealing with at least 3 of those same theorems. We're just going to be looking at them through what we call the converse of each of those theorems. So here in blue, I've written this converse term. This is actually a term we learned in Math 1. We did a unit in Math 1 on argumentation and logic and that sort of thing. And one of the terms that we learned was converse, which if you don't recall, converse means that it's essentially switching the hypothesis and conclusion of a given statement. All right. So for instance, in section 2, a given statement might be like that first theorem where it says, if I have a parallelogram, then the sides opposite to one another in that parallelogram have to be congruent to one another. Okay, so breaking that down even more, parallelogram equals opposite sides are congruent to one another. Okay, that was section 2. The converse of that statement shown here is that now I'm starting with the other piece of information. Instead of starting with the fact that I have a parallelogram, instead I'm starting with a figure whose opposite sides are congruent to one another. And because of this situation, that's going to force this to be a parallelogram. It's essentially deja vu, right? It's the flip side of the same coin. They go hand in hand with each other, to use all those analogies, right? Essentially here, the front and reverse of the same statement are true. In section 2, I start with a parallelogram that forces opposite sides to be congruent. Here in section 3, now I have a figure whose opposite sides are congruent. That's going to force that figure to be a parallelogram. They go hand in hand, right? So the convenient thing here with how that applies to what you're going to see in this section is that it's going to be a lot of the same thing. It's just you're going to see a slight subtle change in how the questions are asked for the problems, and I'll show you what that would look like a little bit later in the notes. But again, this one is exactly the same as the first theorem in section 2, other than the fact that it's just written in converse. In other words, here I'm starting with the other piece of information, namely here I have opposite sides are congruent, then it must be a parallelogram. In section 2, I started with the parallelogram, therefore opposite sides are congruent. The second one is like the second theorem in section 2. In section 2, I start again with a parallelogram. I know something's a parallelogram. That's going to force the internal angles, the angles that are opposite one another, to be congruent to one another. opposite angles must be congruent inside a parallelogram. In this case, now I'm starting again with the opposite information. Namely here, angles that are opposite one another are congruent to each other in this four-sided figure. That's going to force whatever this four-sided shape is to be a parallelogram. Okay, similar to the last one. It's just the flip side of the same coin. So in section 2, parallelogram means opposite angles are congruent. Section 3, opposite angles are congruent means parallelogram. Pretty straightforward. All right, before I go on to the other two, I want to talk over here just really quickly in the margin. One thing you may be asked to do here in this section is, again, the name of this section is proving some quadrilateral to be a parallelogram. Okay, so as these are shown right here, these are just regular quadrilaterals. Based on the information that's shown, I'm going to lead to the conclusion that it must be a parallelogram. Over here in a coordinate grid, I just want to say a couple words about this. In a coordinate grid, we get a unique set of circumstances. As these guys are drawn, there is no, even though it's on graph paper, there's no real like XY axis shown. It'd be considered what we call free space. In other words, there's no real coordinate grid or anything like that. It's simply a shape in space, right? Over here in the margin, it's quite obvious that this is on a coordinate grid. There's an X and Y axis. And why does that matter? Because again, in this case, you may be asked to show, all right, here's a four-sided figure, prove that this must be a parallelogram. And for the record, it is possible to show that this is a parallelogram based on these theorems or the other ones that we'll cover in here. But it's just a little more tedious. It's a little more high maintenance. For instance, if I wanted to start with the fact that opposite sides were congruent or had the same measurement, the same length, to do that in a coordinate grid, I would have to use the distance formula for each of the four sides here using their coordinate points. And that would be pretty time consuming. Not impossible, not actually particularly difficult. It would just be time consuming and tedious, right? You got to take each set of coordinate points, plug them into the distance formula. You would get the correct answer. It would just be annoying to do so, right? It would be possible to measure angles using a protractor, but again, on a coordinate grid, that's a lot more difficult a task. And you'd have to use some trigonometric methods that we have not learned yet in order to really do that effectively on a coordinate grid. So how would you go about doing it on a coordinate grid? The simple thing is this, that we're going to go back to the very root of the word parallelogram, and that's the term parallel. In a coordinate grid, kind of the unique thing in these situations is I can actually quickly show things are parallel, which is actually far more difficult to do in free space, particularly with contained figures like these, especially when they're just line segments. It's really without being told they're parallel. In free space, I can't ever assume it unless I have something else that gives me that information. In a coordinate grid, I can actually just count boxes and find the slope. For instance, this line segment right here goes up 3 units and over 2 units, meaning that this segment right here has a slope of 3/2. This side opposite to it also goes up 3/2, therefore having the same slope, meaning that these two segments must be parallel to each other, simply by counting boxes and showing they're parallel. I would do the same thing with those two opposite sides, showing that each one goes down 1/2. And because both of the opposite sides have the same exact slope, that would force this figure to be a parallelogram by definition, that the fact that it's two pairs of parallel sides. Okay, so just to prepare you, if you come across something that's dealing with coordinate plane, they're doing that on purpose. It's because then you're going to be dealing with measuring slope, because slopes have to match if they are parallel. Anyway, let's move on. Two more theorems I just wanted to briefly cover and talk through before we get into our description of our examples today. Before I get to this guy, let me talk about this one. I'm going to skip to this one first because this is, again, one of the ones that we covered in section 2. It's another one of those flip sides of the same coin. In section 2, we learned that if I start with a parallelogram, I am told this four-sided figure is a parallelogram, then its diagonals must bisect one another. They have to chop each other in half. And I would be able to see that here in this diagram by, you'll notice these dash marks. Sorry if it's a little small, but the dash marks imply that each of those smaller halves is congruent to one another, which implies that if both halves are congruent or the same measurement to each other, that it has been chopped in half. And so that's how you would show that geometrically in a diagram. But we learned that if I start with the parallelogram in section 2, then diagonals have to chop each other in half. In this case, if I have some four-sided figure like this one here, and instead I know that the diagonals bisect one another, or they chop each other in half, that's going to force this four-sided quadrilateral to then become a parallelogram. Okay, again, flip side of the same coin in section 2. In section 2, parallelogram means diagonals bisect one another. In section 3, this guy right here, if diagonals bisect one another, then it must be a parallelogram. Okay, and so the nice convenient thing here with those three theorems now that are basically repeats of each other or converses of each other, I don't have to learn anything new. I just know that it goes both ways. All right, now in this case, this one's slightly different than what we covered in section 2. And I'll explain why, and I'll illustrate why this one is slightly different than what we've covered before. This is going to be actually most similar to this first theorem we talked about with opposite sides being congruent. However, what's going to change here in this guy right here is that instead of having both pairs of opposite sides being congruent to one another, in this case, I only have one pair of opposite sides being congruent to each other. And that doesn't mean that the other pair are not. It's just the beginning information that I start with. Okay. As you can see in each of these given diagrams, I'm told nothing about the other pair of opposite sides. Instead, I'm just given that one pair of sides is congruent to each other. But then I also have these red arrows in both. And in these cases, that the opposite sides that are congruent to one another, if those same sides are also parallel to one another, that's going to force this to then be a parallelogram. Okay. And I showed both these situations because it doesn't matter if it's top, bottom, or side, side. Okay. As long as you have one of these two situations, it's going to be a parallelogram. Okay. So again, this is slightly different than what we covered in section 2, because in section 2, I started with not only one pair of parallel sides, but I was shown that both pairs of opposite sides are parallel to one another. And then it's different than here in section 3, because instead of having both pairs of opposite sides being congruent to each other, in this case, I only have one pair of opposite sides that are congruent to each other. So it's kind of a combo of section 2 and section 3 right here. Okay, so just really quickly, I want to illustrate this because this is what would have popped into my head as a high school student. I'd be like, all right, well, what happens if I had opposite sides being congruent that were different than the sides that happen to be parallel to each other? So for instance, let me jump to the whiteboard here. So just to illustrate again, what we are told is this, is if I have this situation, and I'll just illustrate this really quickly. If I have this situation where I show you that these two sides are parallel to each other, and they also happen to be congruent to each other, that's going to force this to be a parallelogram. That was a very bad segment there. There we go. All right. That's going to force pairs of opposite sides being parallel to each other. Okay, so my question as a high school student would have been like, all right, well, what if I start with this situation instead? Why can't this be true? Where maybe these sides are parallel to each other still, but maybe I knew that these guys were parallel to each other. Why doesn't that then lead to the fact that this is a parallelogram? And the reason this is worth bringing up is because it is important that they are the same sides that are parallel to each other that are also congruent. Because in this case, it will not mean that it is going to be a parallelogram necessarily. And why? Let me illustrate why. All right, so let me give you this situation. I'm going to give you two parallel sides. I'll even tell you that these lines are parallel to each other. Okay. Even if it doesn't look like it, I know I'm not drawing perfectly straight. So anyway, I tell you that these lines are parallel to each other. I'm going to show you a situation where I'm going to draw congruent side lengths that do not create a parallelogram. So for instance, what if I did something like this? And let me actually use a ruler to show you that I am doing congruent sides. Let me do something like this where, let's say I go from here to there. And if you can see the numbers, you can see that goes 3 inches. So I'm going to draw another 3-inch segment that definitely does not make a parallelogram. So let me see, go like, I have to go like this. There we go. So I have just created a shape. It is not a triangle, even though it looks a terribly lot like a triangle. There is a little mini segment over here, but it is quite obvious that this is definitely not a parallelogram. Even though these two sides right here would be parallel to each other, it's very obvious that these two sides are definitely not parallel to each other. And each of these lengths was 3 inches, just to show you that these are indeed congruent to one another. And so that's why it's important that it's the same pair, okay? Because this is a situation that disproves this guy. So this is not a parallelogram. Or I guess I should put the arrow up here just to clarify that. This is not a parallelogram. All right, anyway, that's where that comes from. That's just, I bring that up because that's something I would have asked when I was in high school. And so I'm sure like at least 1 or 2 of you would have been like, wait, why does it have to be the same pair? Anyway, let me get back to our examples. There are only 2 quick examples here for this section's notes. And I'm really just going to talk about them because they're kind of just copied and pasted from what we did in section 2. Because again, it's kind of the same phrasing. It's just I'm starting with different beginning information. So how will the questions be worded differently? It's very subtle from section 2 to section 3. In section 2, again, I would have begun with diagrams that had those red arrows showing that it was a parallelogram. I'm starting with information that I have a parallelogram, and then I can immediately apply all that baggage that goes with it. Opposite sides are congruent, opposite angles are congruent, consecutive angles are supplementary, and diagonals bisect one another. In this section, I'm basically going to be starting with those 4 theorems, or the one I just illustrated with the same sides that are congruent are also parallel. I'm going to start with that kind of information and then infer and work my way back to find out that it is in fact a parallelogram. So how will that change as far as the wording goes? It's going to be very close. You might not even notice, but it's like, all right, so basically solve for variables to show that a given figure must be a parallelogram. It'll be along those lines, okay? It's a very subtle difference in wording. Instead of saying in section 2, here's a parallelogram, solve for the variable based on the theorems. Instead, in this case, now it's like, all right, here is a figure, show what the variable has to be in order to create a parallelogram. Okay. In any case, in this first example, you'll notice that I have lots of information about internal angles. So similar to section 2, I'm going to really care about the thing that helps me most here, namely opposite angles have to be congruent in a parallelogram. So for instance, in this lower left-hand corner, that's a y plus 87 degrees. Okay, so y plus 87 in that lower left has to match the upper right or be congruent to the upper right, being 4y. So if I wanted to set up an equation to solve for the variable, these guys have to match, or I would just say they have to equal one another. Y plus 87 equals 4y. I go about solving for y in the usual algebraic method. Lower right-hand corner, 2x here has to match or be congruent to the upper left, 3x minus 2 up in here. So I would say 2x equals 3x minus 32. Go about solving for the variable using inverse operations, all the normal stuff after that. Okay, not terribly difficult once you're able to set up the equation, but setting up the equation is the important first step. For this last example right here, again, in order to create a parallelogram, you'll notice they have drawn the diagonals within this diagram. In order to be a parallelogram, these diagonals have to chop each other in half. They have to bisect one another. And we see that with this diagonal right here, that with these red dashes mean that each of these little pieces, these segments right here, are congruent or match. And that's another way of showing that this total diagonal is indeed chopped in half because each of these represents a half of that segment. But the same also has to be true for this diagonal. Namely, this upper half up here has to match or be congruent to this lower half here. So I would simply set up the equation that 2x has to match or equal 10 minus 3x. And then again, I would go through the normal algebraic method of solving for the variable. Combine like terms, move stuff away from the variable. Okay. Anyway, that's what you'll kind of see. Just to prepare you for another way this might be worded, it might say like, all right, for what values of the variable will this not be a parallelogram? Nothing actually in that case would change with how I would solve. I'd still say 2x is equal to 10 minus 3x. I'd solve for x. But then I would say, well, in order to be a parallelogram, x has to equal this specific number, the part that I solve for. If x is anything else, it cannot be a parallelogram. And it's just basically as simple as that. Anyway, that covers section 3 on proving a quadrilateral to be a parallelogram. I'll go ahead and stop the recording there.